So what we're going to look at here is rotational energy and how it can be related to a linear energy, specifically in kind of terms of the kinetics. Now, one of the things before we kind of get into this that I'd like you to think about are bowling alleys. And, hopefully you've been bowling at some point in your life, knock over the 10 pins, get a strike, maybe you've hit a perfect game, maybe you've gotten that big elusive 800 series. But the thing that freaks me out at bowling alleys is how the ball is returned back to you. If you're unaware, whenever you bowl and your ball gets down at the end of the lane, maybe it rode through the gutter, whenever it kind of goes behind the mystical screen, what's actually happening is it's getting lifted up like nice and high, and it's being placed into just a very long track. And what happens is the ball just sitting at the top of the track here, the ball is just being rolled down a hill, and then it just comes back down the entire lane, and it normally may run under the lane. Maybe you have a bowling alley where you can actually see it being rolled back to you, and then it kind of just gets right to here, and then it bloop. It just kind of stops. It hits like a little back spinner real quick, and then the ball's just there. This is kind of scary to me, because wouldn't it make sense that the ball is going to go down, and because it's like a nice rolling system and maybe you've waxed the ball a little bit, if this ball comes down with all of this potential energy and now it has kinetic energy, shouldn't the ball go all the way back up? And if you're standing here smiling, having fun, like, yeah, I'm bowling, wouldn't that ball just clock you in the teeth, and then now you got to go to the dentist and have a surgery or something? Like, I don't know. Like, why doesn't that ball just fly out of the system because it started up so high? Like, why does it only wind up like at waist height? Isn't that a little weird? What's going on there? Now, what's actually happening is when this ball is rolling down the track here, the ball is not just sliding. If the ball was just sliding, it would just go down, slide along the track, and it would, kind of bop up really high here. But what is also happening is this ball is beginning to roll. And whenever a ball is rolling, there is now a rotational kinetic energy. So while this initially had some potential energy, just like we did roller coasters, that potential energy due to gravity is some mgh, it will eventually, as it's moving, not only have a 1/2 mv squared as a linear kinetic energy, because it's physically moving down the track at some speed, but it will also have a rotational kinetic energy, which is 1/2, and if we turn this mv squared into rotation, it will be I omega squared. And this rotational energy is actually preventing it from physically moving as fast as it was before, but that some of that energy is stored in rotation. This is also why if you are like a top tier bowler, whenever you bowl and you roll a hook ball, the revolutions per minute, or the RPM that you can gain on the ball, the more revolutions or the faster you can get that ball to spin when it strikes the pins, you're actually going to get more pin action from that because you're imparting more energy into that pin system during the collision. So here are two energies that we care about in terms of kinetics. Our 1/2 mv squared, which we had before, that's just how fast is the object moving. And then our rotational kinetic energy, which is how quickly is that object, which is some difficulty to rotate, I, rotating. And when we take both of these together, those are all the kinetic energies we can have in the system. Now, while we've been using this and talking about bowling here, one of the main things we need it in the world of physics for is pulleys. Previously in the year when we talked about forces acting on pulleys, we just said that the pulley was changing the direction of the force. So if we had a pulley, there could have kind of a force going around it. And we could say like, hey, look, like, there's a weight pulling down here and a weight pulling down here, and that just kind of boils down to a left and a right. What do you want to call positive and negative? But now pulleys aren't massless. Pulleys have some mass associated to them, and they have a shape associated to them. So they have a mass distribution, which means that a pulley like the one seen here in the diagram, the pulley itself has some angular momentum. Or the pulley itself has some moment of inertia, It has some moment of inertia. When it rotates, it can be developing angular momentum, but it has some moment of inertia here. It has some I value because it is a mass with a shape. And that means whenever an object falls on it, like we have this massive block here, this weight, when this begins to fall down to here, we not only have to think about how that potential energy is turned into kinetic for the block, but also how the pulley itself has begun to rotate. So that's what we're going to take a look at here in our example 1. How can we think about the kinetic rotational energy of the pulley, and how we can think about the kinetic energy of the block falling. So to do this, we need to conserve energy here. And remember, whatever energy we have initially is the energy we're going to have final, unless we have some sort of friction or whatnot. We're going to pretend we don't have friction here. Friction makes things like a little bit of a pain in the butt. So this is a 5 kilogram block, so it's got a mass of 5 kilograms, and it is wrapped around a pulley right here, which has that rotational inertia of 0.2 kilogram meters squared. So that is 0.2 kilogram meters squared. And that pulley has a radius of 0.5. So that's got a radius here of 0.5 meters. The block is falling a distance, center of mass to center of mass, of 1.5 meters. Whenever the block is falling this distance, we need to calculate this angular velocity of the pulley. And if we remember, that angular velocity is an omega. So how do we go about doing this? Well, what initial energy do we have stored in our system? Because initially, the pulley is not rotating and the block is not moving. So our kinetic energies initially are 0. But the block is up from some relative position down here. So if this is our reference point where the block will be, and up here is where the block starts, then we know this block has a gravitational potential energy associated with it. And that is going to equal the block's linear kinetic energy, and we'll call this for the block, plus there's some rotational kinetic energy for the pulley. Okay? So if we go ahead and start kind of working this out, for our block, our gravitational potential energy is mgh. Our kinetic energy of the block as it linearly moves is 1/2 the mass of the block times the velocity of the block squared, plus, and then the kinetic rotational energy of the pulley is 1/2 I of the pulley times the angular velocity of the pulley squared. So how do we go about figuring out what this angular velocity of the pulley could be? Well, we know the mass. Let's just see what we have and what we don't have. We know the mass of the block. We know gravity is 9.8. We know the height's 1.5. So this will be some number here. We know 1/2. We know the mass of the block. We don't know the velocity. We know 1/2. We know the moment of inertia is 0.2. We don't know the angular velocity because this is what we're trying to solve for. This is annoying. I have 2 unknowns. I don't know the velocity of the block, and I don't know the velocity of the angular velocity of the pulley. But I only have 1 equation for this. I can't solve for 2 unknowns with 1 equation. I need to pull a second equation in here. Well, something we can think about to do this is what is actually causing this pulley to rotate? It's the block falling. And the block falling attached to the rope, kind of pulling this, means that the block and the pulley are moving together. The linear velocity of the block is related to the angular velocity of the pulley. And if we go back to our rotational ideas, we know that a linear velocity is equal to an angular velocity multiplied by the radius of which that object is rotating on. And in our case, we know the radius of that pulley. It is 0.5 meters. So we can actually get rid of this velocity by subbing in omega r, because the velocity of the block is equal to the angular velocity of the pulley times the radius of the pulley. So we're going to do just that. And when we do this, we will have, let's do this in a different color, we're going to have mgh equals 1/2 times the mass of the block times, and this is our new velocity squared that we're putting in, omega of the pulley times the radius of the pulley. Make sure you square that, which we're actually going to end up squaring both of them, plus 1/2 the moment of inertia of the pulley times omega pulley squared. So at this point, if we kind of loop this back up here, we can start plugging in some numbers. For MGH, we know the mass of the block is what was it? It's 5 kilograms. So we can say 5 kilograms times g, which is our classic 9.8 meters per second squared, times the height it's falling through, 1.5. And that's positive because we started above our reference position. This has to equal, and let's just write this out, 1/2 times the mass of the block, 5 times omega pulley squared, which we're trying to find, times 0.5, the radius of the pulley, squared. And then our last little bit here is plus 1/2 times the moment of inertia of the pulley, which is 0.2, and then the omega of the pulley squared. So now we only have one unknown variable. We can create these coefficients here, add like terms together, then try to solve that. So let's just do the left here. 5 times 9.8 times 1.5 equals 73.5. And even though I didn't put the units in across this here, I know this has to be energy, so it has to be in joules. And let's set up the coefficients in front of each of these omega p squares. So half of 5 is 2.5, and 0.5 squared is 0.25, so 0.25 times 2.5 is going to equal 0.625, so 0.625 omega p squared plus, and then 1/2 of 0.2 is 0.1 omega p squared, so 73.5 joules equals these are like terms, so 0.725 omega p squared. And at this point, we're just solving this with some algebra. We need to divide by the 0.275 first. Get rid of that. And then I need to get rid of this square here. And the way I get rid of a square is with a square root. So we take 73.5 divided by 0.725, because that's all in the square root. We get 101. And the square root of 101 is going to be somewhere around 10. So we find finally that our angular velocity of the pulley is around 10, technically 10.06, but we'll just leave it as 10 radians per second. Okay, so a little bit of math there, but nothing too crazy. The big feature to recognize was that we needed to relate the linear and angular components somehow. For part B here, because we're not done, we need to find the linear velocity of the block. Ugh. Well, this is actually super easy. If we just recall what we just saw, the velocity of the block linearly is equal to the angular velocity of the pulley times the radius of the pulley. We know the angular velocity of the pulley now, and we know the radius of the pulley is 0.5. So in order to find the linear velocity of the block, it's just angular velocity of the pulley times the radius of the pulley, which is going to be 10 rads per second times 0.5 meters. Half of 10 is 5. Remember, you don't actually care about radians when you go into linear, so this is just going to be meters per second, which makes sense for our units of velocity. And that's it. Straightforward. The hard part about that was just kind of working through part A, setting up all of our energies. We had initials equals final, recognizing the link between the linear and the angular, and then working through all of that math. So that was a little bit of math there, a little bit intensive, but it wasn't too bad, and getting part B was pretty straightforward. So that's how we can start thinking about conservation of energy with rotating objects. We can't just think about objects moving left and right anymore. We also need to consider how the objects are rotating, and the fact that that rotation is actually going to take some of the energy needed or that the object may have had initially. So hopefully that gives you an idea of what's going on there. Hopefully you're a little bit less afraid when you go bowling about that bowling ball coming up and hitting you in the face and what's going on there. So with that, we're finished here. You can take it easy. Have a good one. Adios.